What's that? Nothing but business. All right, here we go. I'm only doing this example because Ved asked for it. That's it. Otherwise, we would have skipped it and done less today. No, but because Ved asked, we're doing more. Thanks, Ved. Plus, I'm teaching to a large audience right now, so I really need to make sure. Yeah. Including myself. There are 5 people here. But okay, so anyway, happy senior skip day, guys. Okay, so given our function we want to analyze and sketch, it's a little different because now it's more involved than just like a polynomial. So, all right, first things first, we want to find our domain. Okay, so we would have to look at dividing by 0 or taking the square root of any negative numbers. Is that a possibility at all in our function? Now we're taking the cubed root, and I can take the cubed root of a negative number. That's no problem. But even still, I'm squaring everything anyway. So my domain is going to be all real numbers. And actually, even though I said what I said about range, we can find our domain, or we can find our range right now. What would be my lowest output, my lowest possible output for my original function? 0. Can I get into the negatives? No, because I'm squaring it first and then taking the cube root. And even if I was wrote it differently and which I could do, squaring it last and cube root first, it's still getting squared. So because of that, everything is going to be positive. Can I achieve 0?
Yes.
Okay, so 0 to infinity is going to be my range, including 0. All right, let's do intercepts. So I want to find both my x-intercepts and my y-intercepts, okay? So if I set it equal to 0, what would I get? I'd cube both sides. I'd take the square root. You would still get 0 on the left side, equals x plus 10. So subtract 10 from both sides, and I would get x equals negative 10. So then I have an x-intercept at negative 10, 0. But we also need to find our y-intercept. So let's plug in x for that. So f of 0 is going to equal the cubed root of, so 0 plus 10 squared. But Ross is right, it's just the cubed root of 100. What is the cubed root of 100? It's something. I don't know what number it is, though. Let's see. 3 cubed is 27, right? 4 cubed is 64. 5 cubed is 125.
It's 4.4 or something.
Right. So somewhere between 4 and 5. Okay, so we'll keep that in mind. 4 point something. Okay. All right, so again, on your quiz, you'll be able to use TI-30s. So you can find out exactly what value that is. If you leave it as cubed root of 100, though, that makes me happy. No worries there. Now we need to find our end behavior. So let's take the limit as x goes to negative infinity of f of x and talk about what we would get. Yeah, it's going to be positive infinity, right? Because I would plug in very negative numbers, which end up getting squared, and I'm taking the cubed root of it, so though that hits it down even further, I still will make it to positive infinity at some point. What's the story from the right? Limit as x goes to positive infinity.
Also positive.
Good. All right. Do I have any asymptotes? I do not. No, yeah. It's not a rational function, so I definitely don't have any vertical asymptotes in this case. It's not a square root, so I wouldn't have a hard stop of my domain or anything, which wouldn't even give me an asymptote anyway, so I have no horizontal asymptotes, none. Okay. All right, now I found all of my things from my original function. Let's do the derivative. Before we do the derivative, I feel as if it would benefit us to rewrite the original function.
Chain rule.
Well, yeah, we're going to have to use chain rule for sure. But how could I rewrite my original so it's not such a pain in the butt?
X to 2 thirds.
Yeah. That'll make our life easier for sure. 2 thirds. All right. So then when I do my derivative, I would get 2 thirds x plus 10 to what power? Negative 1/3. Good. All right, and then we do the things. We can rewrite it if we want. So 2 over 3 times the cubed root of x plus 10. And then we would set it equal to 0. Now I get no values for my numerator, right? So my denominator, what would make that 0? Negative 10, okay. Are we okay with just saying that? Do you guys want me to show that? So negative 10 would give me a 0 in the denominator and no other number. Because otherwise, if you set just this piece equal to 0, you divide by 3, cube both sides, you're left with x plus 10 equals 0, so it's just going to be negative 10, okay? All right, now, I want to point this out. Negative 10 makes my derivative not exist. It makes my derivative undefined, correct? What about my original function? It's fine, right? It ends up being an x-intercept, right? Y-intercept, right? No, an x-intercept. Sorry, math is hard. So it ends up being an x-intercept in my original function, so it's defined in the original. So what that means is we can get mins and maxes out of it. Remember how we were talking about like points of inflection, right? Might not be defined because it's an asymptote or whatever. That doesn't happen here. Okay. All right. So if I plug in something to the left of negative 10. Is my derivative going to be positive or negative? It's going to be negative. Because I would have like negative 11, for example. Plus 10 gives me negative 1. Cube root of that is a negative number. And then something to the right of negative 10, like negative 9 or 0, for example, that's going to give me positive values, right? Okay. Which means, what do I have at negative 10? Not. I think one level up. It's going to be a critical number, right? But it's going to be a critical point, a relative extrema at negative 10, because it switches from, I should answer this question down here, right? Increasing from negative 10 to infinity, and then decreasing from negative infinity to negative 10. And because my function is defined at negative 10, I have something. I have a relative extrema. Which one is it, a min or a max? Why is it a min, Max? Yeah, it's going from decreasing to increasing, so it's going to be a relative min. Very good. So negative 10, and then I would plug that into my original to find what my y output is, but I've already done that. It's 0. Good. I have no relative maxes. Okay. All right. Now, here's another question. First period toiled over this. What type of graphical feature do I have at negative 10? Aside from it being a relative min, what does that mean?
Vertex?
It's kind of going to look like a vertex, yeah. But it's not like, it made my derivative not exist. So we need to think about what values, what type of... So it's one of two. It's either a vertical tangent line, or what's the other possibility?
Asymptote?
Not an asymptote. Good guess, though. What'd you say? No, it wouldn't be a horizontal tangent line because my derivative is undefined. Not a double zero. Good guess. It's kind of going to act like a double zero. You said what? The pointy stuff. What do we call that?
I don't remember. Like the curved, like, I don't know. I don't remember.
I don't know why I'm doing this. Sharp turn.
Sharp turn.
Yeah.
Oh,
The pointy stuff. Sharp turn. Yeah. Yeah. So there's it's either a sharp turn or it's going to be a vertical tangent line, because it's a great question. It's because we would need to think about, back to like when we talked about differentiability, we would need to think about like what makes our derivative not exist. And it would either be like an asymptote, of course, but an asymptote would make my original function not exist, right? This one, like negative 10 is defined in my original, but not in my derivative. So it has to be one of the other ones. So those were vertical tangent lines or sharp turns. And in this case, well, we'll see. I'm not going to say anything. Do you guys know which one it is yet? It is a sharp turn. Yeah. But we'll look at why that's the case. Okay? All right. Concavity, we got to do second derivative. So I'll circle back to that point here in a minute. Let's do second derivative from right over here. All right. So chain rule again, but it's like the light version of chain rule, right? There's not much going on with it. So negative 1/3 multiplied by 2/3 would be negative 2/9. And then x plus 10 to the negative 4/3 this time, and then multiplied by the derivative of the inside, which is just 1, so I'm not even going to show that. All right, take a second to rewrite, because I feel more comfortable solving this when it's a fraction. Cubed root of x plus 10 to the 4th power. All right. So if we set that equal to 0, we get the same story as the last one, right? Nothing from my numerator is going to make it 0. The only value I need to pay attention to is negative 10. So again, I do the number lines that you guys love so much, and we plug it in. Now, if I plug in negative 11, I would have negative 11 plus 10, which is negative 1. But then I would raise it to the 4th power. So it'd be positive 1. I would take the cubed root of that, still positive 1, multiply it by a 9, and then that all gets divided from negative 2. So negative 2 in my numerator. So what sign will I have? Negative. What about to the right of negative 10?
Also negative.
Also negative. Very good. Okay. So because of that, I would say that, let's talk about concavity. Okay. Concave up or concave down?
Concave down.
Of course.
What?
My question to you guys is, do I need to split these intervals, or can I write it as one? Because it's concave down everywhere, right?
You can write it all together because 9 and 10 still pass each other.
Very good. Very good. We can write it all as one interval because negative 10 is defined in my original function, so I can just say it's concave down everywhere. Good job. It's negative infinity to infinity.
No points of inflection.
No points of inflection because it doesn't change concavity. All right, let's graph it, just for vid. All right, so negative 10 is a thing. Negative 10 is 0, actually. I know what that point is. And then we also have an intercept at 0, and then the cubed root of 100, which we agreed was somewhere between 4 and 5. So here-ish. Okay. Now, if I try to graph the right side, it is increasing from negative 10 to infinity, so I know it's going up. But it's going to be concave down. So it's going to spill water. So it's not going to look like this. Instead, it's got to do like the opposite kind of thing. So it's going to look something like that. And then the left side, I mean, shoot, it's also concave down. So it has to have the same shape where it's like spilling water. So it's going to look something like this. Because it's increasing as well, too, from... or I'm sorry, it's decreasing from negative, so left to right, negative infinity to negative 10, it's got to be decreasing. So it's got to come from above and go down. So it's going to look like that. Now, one thing that changes that, or what that could change that, in my original function, if this square wasn't there, what that's doing is it's taking all my outputs and making it positive, right? So imagine that square wasn't there and I was just taking the cube root. Well, how would that change what our graph looks like? These values wouldn't be positive. Instead, it would almost like... down. It would almost like reflect, right? And then if that was the case, then your graph would look like this, which would give you that vertical tangent line at negative 10. So it would still make your derivative not exist, which we could see that by thinking, okay, if I'm raising something to the 1/3 power, if I subtract 1 from the exponent, that will create a denominator in my first derivative, which that 0 would make my derivative undefined. So vertical tangent line is what results in that. Okay, so sharp turn. All right. Questions there? Cool. All right. Now, what I'm going to teach you now is content that will be related to the next quiz that you guys will take. So after this one that you guys take tomorrow, this stuff will be related to that. Okay? And the first thing we're going to talk about is what is called our second derivative test. Okay? So even before I go into this, let me ask you guys about this. Our second derivative tells us what about a function? Yeah, so concave up versus concave down, right? All right, so let's say we have something that is concave up. Its graph looks something like this, right? Whatever that interval is. So let's say it's concave up on the interval from A to B, okay? If I have a relative extrema that occurs in an interval that is concave up, what type of relative extrema would I have? It's got to be a min. If my function lies above its tangent lines, I'm going to end up with a min. Doesn't have to be at the axes here. It's just how I drew that graph. But this is going to be a relative min on an interval that is concave up. So let's say that's C, whatever. We have a relative min there. Okay. Instead, if I have a graph that's concave down, my extrema occurs here. What type of extrema am I going to have? Good. Relative max at C. It's got to be that way, okay? That's what my second derivative test says. If you have a critical number, which again you get from your first derivative, and if you plug that number into your second derivative, not something we've done yet, but if you plug a critical number into your second derivative and it's positive, that means your graph, F, is concave up, and so you have to have a relative min at x equals C. And then if you plug a critical number from your first derivative into your second derivative and it's negative, that implies that your graph is concave down on the interval that contains that value, so you'll have a relative max at x equals C. And if you plug that value into your second derivative and it's equal to 0, your second derivative test is inconclusive. It could be a min, could be a max, could be neither. You got to use your first derivative test in order to figure it out. Okay? Okay. All right. So we're going to do some examples where we do exactly that. We just do what's called the second derivative test to determine whether our relative mins or maxes, or whether our extrema are mins or maxes. So here's the process of using second derivative test. You still take your first, well, of course you got to take your first derivative, but you still set your first derivative equal to 0 to get those candidates. And then you take your second derivative and you plug the candidates from your first derivative into your second derivative to find out whether it's positive or negative. Okay? All right. So f prime of x all right, easy money, 3x squared minus 12. Though I need to go to my second derivative and test the values in my second derivative, I still need to set this equal to 0. So factor a 3 out, set it equal to 0, and you get x equals plus or minus 2. So those are my two and only two candidates for relative extrema. Now I take my second derivative and I test those candidates in my second derivative, okay? So if I take my second derivative, I get 6x equals 0. And honestly, I can just do this. Like, I don't even need to set up number line nonsense. I can just do f double prime of 2 and f double prime of positive 2, and then just see what sign we get. So if I plug in negative 2, I get negative 12, which implies f of x is concave up or down? Because my second derivative was negative, which implies I have a relative what? Max. So think about the shape of a concave down graph in your head. I have a relative max at negative 2 something. I got to plug that into my original to figure out what my y-coordinate is. We'll do that in a second. All right, and then if I plug in positive 2 into my derivative, I get positive 12, which implies, it's supposed to be an arrow, by the way, not a smiley face, that f of x is concave up, which implies I have a relative min at 2 something. All right. So let's plug those values into my original and then see what we get. So if I plug in negative 2 cubed is negative 8 minus 12 times negative 2 is going to be plus 24. So 24 minus 8 is going to give us 16. No. Yeah? No, that's not right. I made a mistake. It should be 8, right, because it's 16 minus 8. That's my bad. It should be 8. All right, let's try it again. If I plug in 2 cubed is 8, and then minus 8, those cancel out. So negative 12 times 2 is going to give us negative 24. Questions there? Yay. So second derivative test can be pretty handy because then we don't need to like find intervals. If it's easy enough to take your second derivative, just do it, plug it in. I'll let you guys pick. Do you want to do another cubic, a negative cubic, or do you want to do a quartic? Quartic it is. So let's do the same thing, but let's work with f of x equals x to the fourth minus 2x squared. All right, let's derivatize it. It's not a word. Factor out of 4x, x squared minus 1. So we factor it. I don't know why I factored it all the way out this time, but either way, we get that x equals -1, 0, and +1. So those and only those are my candidates for relative mins and maxes. All right, so now we got to take our second derivative. All right, 12x squared minus 4. Pull out a 4, I guess. 3x squared minus 1. Set that equal to 0. So I get plus or minus square root of 1/3, or plus or minus square root of 3 over 3. Okay with that? Add 1, divide by 3. You can divide by 4, ignore that. Add 1, divide by 3, and then take the square root, so square root of a third. All right, so then what I need to do is take those values and plug it into my first derivative, okay? Now you can do this one of two ways. Plugging in square root of 3 over 3 is not super easy. Would you guys agree? So the other thing that you guys can do is you can just make a number line and say negative square root of 3 over 3, positive square root of 3 over 3. And then find your concavity, and then just figure out where -1, 0, and 1 fit into that mix, okay? Square root of 3 over 3, is that bigger than 1 or less than 1? Less than 1, good. Because square root of 3 is like 1.73 or something like that. I can't remember exactly what it is. So then you divide it by 3, and it's going to be less than 1. Okay, so then let's plug in our values and see, or let's actually just figure out what our concavity is. So if I plug in 0 into my second derivative, just start in the middle. If I plug 0 into my second derivative, am I going to get a positive? Yeah, I get negative. Okay, good. And then to the right, if I plug in, like, I don't know. I mean, shoot, we could just plug in -1 and 1. It actually would have been easy to do that anyway. But, okay, if I plug in 1 or 2 or whatever it is, to the values to the right of square root of 3 over 3, is it going to be positive or negative? Positive. And then if I plug in any equivalent value to the left of negative square root of 3 over 3, I'm squaring it. So I'm still going to end up with positive numbers, right? So again, pick a number, plug it into your second derivative. And honestly, I wasn't even thinking about it, but I could have just plugged those into my second derivative, which are easy numbers to plug in.
Can you just do that instead of
Yeah, yeah, absolutely. So like it would have been easier for me to be like f double prime of -1, f double prime of 0.
That's what I was starting to do, and then you like did that.
Honestly, it's because I made a mistake. And in my head, I'm like, oh, I got to plug in square root of 3 over 3. That sounds terrible. But no, those are our benchmarks. That's what we use to reference. So no, if I plug in -1, it's positive. If I plug in 0, it's negative. And if I plug in 1, it's positive. And you can see that by plugging it into here. So 1 squared is 1 times 3 is 3 minus 1, 2, multiplied by 4, you get a positive 8. So, all right, so what does that mean? What do I have? Yep. And then as far as my extrema goes, because the goal is to figure out what type of extrema I have, right?
1, -1, and a max of 0.
So I have what at 1 and -1?
A min.
So a relative min, because it's concave up, right? Concave up, concave down, concave up. So I have a relative min at -1 something and 1 something. And then I have a relative max, because it's concave down, at 0 something. 0 is easy. It's just going to be 0, 0. You plug 0 into your original. Plug 1 into your original. 1 minus 2 is going to give us -1. And then you would get an equivalent value for if you're plugging in -1 because you're raising it to even powers. Okay. Questions there? All right. Let's talk about oblique asymptotes. So we already had a brief discussion at the beginning of class today about oblique asymptotes, and it seems like maybe we've got a little bit of experience, but at most a little bit of experience, right? Let's talk about vertical and horizontal first. Where do vertical asymptotes occur for a rational function?
When the denominator is equal to 0.
Very good. So when your denominator is equal to 0, and then to add on that, if you can't like cancel that 0 out in the numerator, you know what I mean? Like if it cancels factors out, then you get a whole. But if your denominator is equal to 0 and it doesn't factor out from the top, that's when you have a vertical asymptote. What about a horizontal asymptote? That depends upon what?
The
Highest exponent of both the top and the bottom, right? If the degree in the denominator is larger than the degree in the numerator, 0. Very good. If the degree of the top and the bottom are the same, it's the ratio of your leading coefficients. And if the degree of the top is bigger than the bottom, then we would just say,
It's positive or negative infinity.
yeah, because we have no horizontal asymptote, right? However, if the degree of the top is 1 larger than the degree of the bottom, you have what's called an oblique asymptote or a slant asymptote. So reference number 2 from that graphing practice worksheet that I gave you guys on Friday. That is what a slant asymptote will look like. If you guys turn around and look at the board back there, you'll see that there is a line, like Max even put in there, or Machi, a dashed line showing that your graph is going to trend along those values, okay? All right, so the math mumbo jumbo that I have up on our number slide is if you have a rational function, p of x over q of x, and it equals ax plus b plus capital R of x over q of x, if the degree of p of x is 1 more than the degree of q of x, then the graph has what's called an oblique asymptote at y equals ax plus b.
Do you want us to memorize this?
That mumbo jumbo you don't need to memorize. What you do need to memorize is this. How do I find that slant asymptote? I wrote this in a very specific way, and I chose R of x and Q of x to try to give a hint to you as to how we find what that slant asymptote is. You said what?
divide the,
How?
with like division or whatever.
We have to use polynomial long division to get it into, don't sigh, to get it into this form so that we can find what our slant asymptote is, or our oblique asymptote is.
Mr. Pacific.
Yeah. I know, I'm excited too. I know. Let's do it. It's been a minute, right? I understand. My division algorithm is not the best. So, like regular division, it's not the best. But we can do it. Polynomial long division is no problem. We got this. Okay, so we got this. Given this function, we just want to find what our slant asymptote is. What goes on the outside?
X plus 5.
Yeah. And then on the inside, our numerator, right?
Plus 2x minus
Good. Now, do we remember how this goes?
1. Don't we do like 4x first?
Mm-hmm. But where's 4x come from, Machi?
It's 4x squared, so you want to match it with
The first term?
You
Yeah,
have to
first
put
term.
4x in there and
Yeah.
5x plus 5.
Good, because the goal is to cancel something out, right? So I need to figure out what do I need to multiply x by in order for it to equal 4x squared. And the answer to that is 4x. Where do I put that 4x?
On the top.
Good. Above what?
2x.
Keep everything in line, put it above 2x. Because we've got linear terms that we'll try to keep in columns. And then what do I do with that 4x?
Multiply x is
Mhm. I multiply it by both terms, x plus 5. So 4x times x gives me the 4x squared that I was after, because I want to cancel things out. And then I do 4x times 5 to be plus 20x. And then I... Very good. Ved, have you seen this before?
Yeah.
Okay. So my 4x squareds can't... So here's how I do it. Math teachers do it... Some math teachers do it differently. I put what we found on the inside of parentheses here, and I put a subtraction sign in front of it. Okay? So my 4x squareds cancel out. And then 2x minus 20 is going to give me negative 18x. Then what do I do with that negative 17?
bring it down.
Bring it down. And then I do it again. So what multiplies by x to be negative 18x?
Negative 18.
Good. That goes above the negative 17. And then I multiply negative 18 by x plus 5. See, I even wrote the 8 with a heart up there because that's how much I enjoy doing this. So negative 18 times x is negative 18x. And then negative 18 times 5 is negative 90. And then I'm going to subtract. 18s cancel out because negative 18 minus negative 18 cancels out. Negative 17 minus negative 90. It's like negative 17 plus 90. 73. And what is that?
It's the
Remainder.
Good. So we would say plus 73 over x plus 5. Now, if you look at that part that Rasika was like, do I have to memorize that? Our oblique asymptote is y equals ax plus b, which is this part right there. I do not care about the remainder. I don't care about that. All I care about is the part that you get across the top, okay? So my slant asymptote is y equals 4x minus 18. And then when it comes time to graph that, you would graph the line y equals 4x minus 18 just as like a dotted line, and then that is what your slant asymptote would be. Okay? Could we do one more of those where we actually like give it a little sketchy sketch?
Yes.
Yeah, let's do it.
Sketchy.
Sketchy sketch. All right, so it says find the oblique asymptote and provide a sketch. I'm not going to make you guys do all the things, but I do at least want to find what the asymptote's going to be. And then I want to talk about what the graph could possibly look like. All right, so let's find our vertical asymptote. Like let's just run through the whole asymptote question now. So vertical asymptote's always the easiest place to start. Am I going to be able to factor that numerator? No shot. So my vertical asymptote would be what? Yeah, so negative 4 is my vertical asymptote. Would I have a horizontal asymptote?
No.
No, because my degree at the top is bigger than the bottom. So that creates our opportunity for us to have a slant asymptote. And again, I don't know if I mentioned this clearly enough, but the degree of the top only has to be, it can only be greater by 1. So if it's greater by 2, then I'm not sure if there is like a slanted asymptote that would trend in, instead of a linear equation by the difference of 1, like a quadratic equation. I've not done enough functional analysis to know whether that's the case. So we only look at cases when the degree of the top is bigger by 1. All right, so we're going to have one. So we got to do polynomial long division. And again, I try to figure out, okay, what multiplies by this term to equal this term right here?
Negative x.
Okay, and I put that above my other linear term. And then I distribute that to everything out in front. So negative x times x is negative x squared. Negative x times 4 would be minus 4x. And then I subtract. So my negative x squareds cancel out. Negative 2x minus negative 4 would be positive 2x. And then I bring down that plus 7. What multiplies by x to equal 2x? 2. So then double everything. 2x plus 8. I forgot to do that during first period. I was embarrassed. So then I subtract. My 2x's cancel out. 7 minus 8 is -1. Which is what? Yeah, so I don't really care about that part. What I care about is this part right there. So my slant asymptote is going to be y equals -x plus 2. So now let's get that into some sort of graph. So vertical asymptote at x equals 4, and then slant asymptote at -x plus 2, so y-intercept of 2. And then I'm going to go up 1 over 1, up 1 over 1. So that isn't the best line, but let's say it looks something like this, okay? Now here's what I want to make abundantly clear. What will my graph look like in light of what we've just found? Okay, so your graph's going to run along the asymptotes, okay? This isn't always the case, but typically it'll fall into one or two cases. So it'll either look like this, and then symmetrically this, or your graph will look like this and this.
Could it be all of those?
No, because it wouldn't pass a vertical line test.
Okay.
But it could be like this and this. It's possible that it could look like that. And then conversely, it could be like the opposite of that as well too.
And you only know that if you do the first and second derivative then? Cavity and
Yeah, that, or let's do it without it. We could just pick test points. So for example, like if I found my y-intercept, super easy, plug 0 in for x, what would you get?
the 7.
Is that bigger or smaller than 2?
Small.
Okay, so it'll probably be like right here, right? So what that tells me is my graph is probably going to live in this area on that part of the graph instead of up there. You know what I mean? So you're right, though. You need to pick test points. Like that's my only way to determine that is by picking test points. Okay? Cool. All right, your homework is scattered between 2 pages. So like 253 has 3 different things on it. I don't know why in the past it was broken up into different pieces like this instead of like one cohesive value, but I think it's to like try to get all the main pieces together. So I think 25, 29, 28, and 32 are maybe graphing. I can't remember off the top of my head. You're doing second derivative test on 242 for 23 to 26. And again, the stuff that we did today is like, you know what your quiz is tomorrow already. I talked about that a ton. So you know what that's going to look like. The rest of the stuff is going to be on our next quiz. I don't exactly know when that is yet. I got to sit down tonight and do a little bit of planning. So, yeah. And then I told first period, don't worry about 46. If we want, we can do that in class. And then 17, 20, and 21, you guys are just finding oblique asymptotes. Okay? I think I do have some more material to practice slant asymptotes if you guys are struggling with it. Like I have like a worksheet I think I can give to you guys.